Alrighty, guys. It's the Data Daddy here, and as always, I just want to start out by saying thank you for taking interest in my channel. I really hope that you guys find this content useful, and if you do, I'd really appreciate it if you hit that like and subscribe button so I can continue to grow and provide you guys with more quality content. Okay, now we got that out of the way. Let's get down to business, and this is our second. I know it says part one, but we had a part zero of the series where we talked about just a general overview of optimization in data science, what some of the differences are with the major flavors and how they kind of work together, and how we kind of looked at like what problems each of them solved. So now we're going to take that a step further, and we're going to go and we're going to take each of those we talked about, and we're going to go through it a little bit more in depth, and we're going to put some code to it and see, how these things, the mechanics of how this actually works. So first and foremost, as we said, gradient descent is kind of like the backbone, or like the building blocks of everything else. So we're going to start there. And just as a reminder, I think I've said this in some other videos, but we are going to be, or I'm going to be using or referencing this textbook quite heavily. And this is a textbook from Dr. John Miller of UGA. Full disclosure, he is actually one of my professors, and so I've been used this in several classes, and I really like the textbook. I think it does a great job. So I'll be using stuff from it, and I just wanted to reference that. And here it is. There's a link if you want to go check it out yourself. And I'm specifically looking at today the Appendix A section, starting in page 619. Sorry. And that's basically just optimization data science is what that appendix is devoted to. Second thing to note is, really with neural networks in general, and especially with optimization, we really, you need to at least have a basic understanding of calculus, linear algebra, vector calculus, and specifically like derivatives in the chain rule. So we're using a lot of that. Optimization really is taking the derivative. It's just a question of what order we're taking. And good news is most of the time in data science we're looking at the first order, so that's a little bit less complex. But either way, it's a good idea to go through and brush up if you're not familiar, or make sure that you understand these basic concepts. And there's some great YouTube resources out there, and there's some stuff in the textbook that helps. So anyway, just go back, and if you're not familiar, and I'll do my best as we go through to kind of make it clear. But if it's not, may need to go back and review some of these concepts that we use to build these. Okay, so without further ado, let's start getting into it. So gradient descent, what is it? It is an algorithm, an iterative algorithm that solves or seeks to optimize a function using the first order derivatives, or first iterations of first order derivatives. That sounds kind of fancy and complicated. Basically, what we want to do is we want to take a function like this, and we want to keep solving or keep adjusting our input values so that we can iteratively move closer and closer and closer to ideally the optimum, or the global optimum solution. You can see here. So basically, what this would look like is we would start out with some sort of initial guess for x. This could be, a vector or a matrix or a single value, and we'll talk about that as well. But some input, and then we want to get an output and see where that. So as an x, imagine this is just x and simple x and y. So put in, say this is x equals 1, and that gives us a y of maybe that's 5. Okay, and then we plug that in and update, or we plug it into the gradient descent function. We get out, we find a new x value, which is a lower y. So we're slowly dragging that down to the lowest y we can find iteratively, and then eventually we decide that, okay, this is the best solution. So it's really a high-level basic view of what we're really trying to do with gradient descent. Okay, and we said it's first order, so we're just looking at basically, if this was our function, we would differentiate this function, and then we would use the these inputs to give us values for the slope, and we want where the slope is flattest. So if you take the slope here, you can see the slope would be 0. So that would be the minimum slope, and ergo, once we found the minimum slope, we know that we have minimized this function. Okay, so why do we need it? And in data science, we use it to fit parameters in models. For example, like we would use the quality of fit measure like sum of squares, and we want to minimize that. There are different different parameters that you can minimize. For example, you could minimize sum of squares. You could minimize a whole list of things, really, but it depends on whether you're doing classification or what have you. But you could use L1 norm, L2, and this is L2 is this sum of squares, and the alternative would be like the Manhattan distance, where instead of squaring it, you just take the sum of the errors. So that's another option you could do as well. But typically, sum of squares is the most common. And like I said, gradients are involved in most cases, and in fact, with gradient descent, they'll always be involved. And then one of the things too that I want to address is why can't we just use a basic linear algebra approach? Say, for example, rather than using this iteratively, why can't we just set up a system of equations and say, okay, we're going to set these equal to 0, or we're going to set the gradient measure equal to 0, and we're just going to solve deterministically for those parameters. Why can't we do that? Why can't we do that all the time? And I guess in reality, you could do it all the time, and you could just solve everything with linear algebra. However, where this becomes complicated and where this doesn't really work for data science and machine learning is the fact that, say, what if you had a million plus rows of data, and you had 100 or 1,000 or 10,000 input features or input parameters that you're trying to run through this model. Well, imagine what kind of a matrix that would be. Imagine trying to set all of that equal to 0, and then invert the matrix or use LU factorization or one of those techniques to actually solve. You wouldn't have enough RAM. Your computer would probably catch on fire. It could be done in theory, but in practice, in reality, it's not possible. So that's why we need these iterative optimization algorithms, because we can't really deterministically or directly, we should say, we can't really directly solve, a system of like you normally you could take, like, say you had a system of equation with 3 values and then 2 and then 1, and then you set it equal. You take the LU factorization and you can figure out what your parameters are supposed to be, or what the optimum parameters are actually supposed to be to get everything, the gradient, to equal 0. Well, like I said, not always possible when you have these really large, ridiculous problems like we sometimes have in machine learning. So, important point, just wanted to highlight that as far as the reasoning why we actually care about gradient descent so much in data science. Okay. Like I said, it becomes computationally expensive. So all this is kind of spelled out here in these notes. Another thing too, gradient descent allows for parallelization and distributed calculations across processors. So, you may have heard of Apache Spark, or people using GPUs or TPUs or things to speed up these computations, and that can be done. If we're inverting a matrix, say, we wouldn't be able to do or run these operations in parallel, but with this we can. We can run iterations in parallel. We can distribute the actual computations across multiple processors, and all this is an attempt to speed it up and make things faster. So that's another benefit of using these iterative algorithms and gradient descent in particular in this case. Okay, so now how does it work? And this is kind of a high-level example. And in fact, there's a really great tutorial. I really love this guy. His name is Josh Starmer from StatQuest. You may have heard of him, but he does a lot of stuff with data science and statistics as well. And he has some really great visuals, and he really goes sometimes almost painstakingly slow in some of these descriptions, but he has a really great video on gradient descent. And actually, he shows, from a very simple case, how this works with great visuals and everything. So I recommend if if my explanation in this case isn't good enough, I would definitely go and watch this video because it will really help you out. Okay, so now how does it work? I said it before, it was iterative, so this is kind of some pseudocode here where we're discussing, what that actually looks like. So we're saying repeat until convergence. So convergence means, we get to a point where we are satisfied, or in this case, where we have reached the global optimum solution. Okay, so, and this is different notation than we've seen in the past, especially if you're, following my other series on, neural nets from scratch. This is quite a bit different. This is more conventional notation. Actually, the book has some fairly odd notation, but this would be that weird h bar variable that we talked about in like perceptrons, for example, for the objective function or the cost function. And really, but you could think of it as it doesn't have to be a cost function in terms of data science. It could really be any function, and that's why I made a general example today, not really specifically related to data science, because I want to show that this can be used as it's a general optimization technique. It's not specifically for data science. It just so happens this works very well for data science. So anyway, so this is our inputs, or it could be, and again, I'll talk about this here. So this could be a matrix, it could be a vector, it could be a single point. And today we'll treat this as just a single, like I said, it would be a very small array. So this is, for our purposes today, this is going to be a very small array. So this would be like maybe 1, 2, 3 in a list, or in our case, it'd just be one variable or one input and another input. And anyway, so that's our original, and then we're going to take the original and then we're going to update it in some way based on what is optimum based on the gradient. So as we can see here, so this is the partial of our function, and then we're putting in 2 inputs. So in this case, imagine this is xj, this is a vector, and then we have 2 values in the vector. So we'll just call this, let's say that, let me draw this, it might be easier to understand. Okay, so let's say that this is our theta. Okay, and this is going to equal a input vector, and remember, a vector is just an array of values, so we'll just say this is 1 for our purposes and 2. Okay, so we're saying we're going to plug this in the partial, or the dot product of all the partials of said function, or whatever this function is. Oop, where'd you go? Where'd you go? There we go. Oh, sorry guys. Okay. Into the input of this function. Okay, and that's gonna tell us how we need to change, or what amount of change we need to apply back to this original input. And then that's going to be scaled or weighted by the learning rate. And this learning rate is just kind of like a way to throttle the amount that we move. So for example, in the beginning, in theory, when these are inputs are large, then we're going to take big steps. And then as we can move closer and closer, and then this value gets this value, man, I wish I could draw on this, but anyway, basically this value, if you imagine there are brackets around this value multiplied by this, as this decreases, well, so will the amount that they actually hop, because this is going to scale it. So anyway, all that to say is that we're going to iteratively update every time and just get closer and closer and closer and closer until we arrive at supposedly the globally optimum solution. Now, it's not always the case. Sometimes we might get stuck, sometimes the curve might be crazy and we think we're at the global optimum, but we're not. And we don't know. That's where stopping rules come into play, and there's a lot of other stuff that comes into play later that will help us to make sure that we arrive at the optimum, the global optimum solution. But for now, in this naive approach, we're just going to say that, okay, if we find the minimum, the quote minimum, then we're done. And depending on how we set this learning rate, the steps can either be small, and that will help us, converge, or if we set it too large, we might overshoot. We might jump from here all the way to here, and we miss the solution, and then we do this weird thing where we keep flip-flopping back and forth, and we never actually can converge. So the learning rate is very important. The learning rate will help us converge, and this is a hyperparameter that we can tune to help us move towards an adequate solution. And we'll see. We'll go later when we actually put it in code. We'll tune this and we'll tweak it so that we can, see this and how we can actually find the optimum parameter. Okay. And now just to formalize the steps here, we want to initialize the input weights, and really this can be done any way that you want, but you could randomly do it. You could just assign it to 0. You could put some value you think that's going to lead it, make it converge faster. So for example, maybe you have some inkling that this is the minimum, and you could just set it here, which is way closer than here, and it'll converge much faster. But if you don't know, and most time you don't know, so you just would anything is fine because it just gives you a place to start. All right, and then we calculate the gradient, and that we kind of go into actually calculating the gradient in another video, and I can't remember if we do it here or not, but basically it's definitely in neural networks from scratch, and the perceptrons specifically for sure, but it may also be in this. I don't know if I've included it or not, but basically just take the partials and the dot product of them, and then boom, we have our gradient. Okay, and then we adjust the weights with the gradients. So again, imagine this is the gradient, and then we're multiplying it by our eta, and we're getting our gradient, and then we're adjusting our original weights, or our inputs in this case. And I'll use those two synonymously because weights is associated with like data science problems, and then inputs is associated with just general optimization. But we're adjusting whatever value we're throwing in, we're adjusting it. And then we repeat this iteratively until we can finally come to the optimum solution. Okay, and then we already talked about there are two flavors, pure and batch. And today we're going to be updating for every instance. So we're just going to take the pure approach, is keep it as simple as we can. Okay, and now this is best explained at this point from an example. And I took this from the book. I believe this is the end of the first section of the optimization appendix, which I listed above, but I literally copied it straight out. So this is we want to minimize this function. Okay. And again, this is not in any way related to data science. It's just a general function that I guess whoever wrote the textbook, Dr. Miller, just pulled, out of his butt maybe, I don't know. But it's just some function that we're trying to minimize. And I went on to Desmos and I graphed it, and this is what it looks like. So it's this kind of, ice cream cone looking shape with a rounded nub. So ideally, the minimum is at this, whatever the bottom of this nub is right here. So we should be able to, with gradient descent, start somewhere along this cone and work our way down and find this optimum solution. So that's the goal. Okay, so like I said, first we want to initialize our input weights. So I just used NumPy, and I just said, okay, we're going to initialize. I just kind of looked at this and cheated a little bit. I looked at the slope, and I said it looks like it's between 0 and 10. Those could provide some good values. So I just initialized, 2 inputs. So again, this is our array, our input array, and it only has 2 values because we only have an x1 and an x2 in this case. So we can't just have one input. We need a vector or an array of inputs. So, we're picking 2 random inputs and sticking them in an array between 0 and 10. Okay, so now the formula for gradients. Okay, so we take this function, with the inputs. In this case, we have 2, so this would be x0 and x1. It's just, notationally this formula that I stole says x and y, but really it's just two inputs. Okay, so for us it's going to be this, and they would go here. And then we want to differentiate, or take the partial differentials of this equation with respect to x and with respect to y. And then we want to add them together. Or not add them, but we want our own vector of partials, basically, for the gradient. And we'll see what that looks like in a second. I did it with SymPy so we can actually see visually what's going on. This is another really cool thing. Python will actually differentiate, integrate, and do these things symbolically for you. So that's I thought this was a pretty nice way to show it with some code. So let's go ahead and initialize this. All right, so it looks like our initial values are 9.6 and 3.71, or sorry, 9.06. All right, and then we're going to import SymPy. And then I linked the documentation here. I'll include all these links. I'll include them in the description of this video, so you guys can go check them out. But basically, we can initialize x as the symbol x, y as the symbol y. And then this is the f, supposed to be abbreviated for f of x. So f of x, this is the same function that we started with up here. Okay. The only difference is we're going to let x1 equal x, and we're going to let x2 equal y. Oh, I'm sorry. I think I called this x0 earlier, but in as terms of the problems, it's x1 and x2. So I apologize. So this is x1 equals x and x2 equals y in this scenario. So okay. So same thing, we're just subbing in x and y for x1 and x2. Okay, and now we want the partials for the partials of that equation with respect to x and the partials with respect to y. And this is just how SymPy likes it to be written. Okay, and then we're going to take those outputs and we're going to stick them in an array or a vector or whatever you want to call it. So Python, it's an array. But I like to call it a vector. It just depends on what you want. But basically, it's in Python, for all intents and purposes, it's just an array. So there we go. So now we have an array of 2 times x minus 8, which is the partial with respect to x, and then we have 2y minus 4, which is the partial with respect to y. Okay, and then we just stuck that in a vector, and now we have a gradient, which is a gradient literally is just a vector of partials. Okay. So now we want to make a function that returns the value from the gradient that we gave. So basically, if we give it x and we give it y, or sorry, if we give the function the gradient, we want it to actually solve with that x input and the y input and return us what that value is. So basically, if we give this if we give the our original x and y inputs, so if we give this and this, we want to know all it's going to do is take those and plug it into this this partial derivative that we just calculated. So for x, it's going to plug it here. For y, it's going to plug it here, and then it's going to save those values and then return them. So let's do that. Okay, and then let me actually just print it out. Let's go ahead and print this, just for giggles. Print grad, so we can see what's going on here. Oh, I'm sorry, we haven't called this yet. That's why. So, never mind. I think it actually prints in the other function, but so we don't really need that. We're gonna call it later. Okay, so just hold on a second. We'll see that in a little bit. Okay, so now we're going to update the inputs. And again, this is equation I stole from this textbook, and I believe it was in the summary as well. But basically, it's the same, or very similar, to this guy. Just, again, a little bit different notation. So again, this is our input. Taking our input, we're subtracting it from the learning rate, which was, I believe, alpha earlier, and now it's eta, which is this weird looking n thing. And then again, this is the gradient of the function, which we have here. So the gradient of the function and then we're going to update the weights. So, okay. And this is a function I made so that basically it takes the gradient we calculated here, and then it just plugs in an eta we set, and then it just subtracts a parameter. So this is really, it should be probably called update weights or update inputs, because it just literally plugs our values, so our x input and our y input. It plugs it into the gradient, it gets the gradient, and then it just multiplies the gradient for each respective gradient. It multiplies it by its respective input, subtracts it from the original, updates, and then returns it as a list. So gradient, update parameter, and then finally we want to put this all in a loop. So I just said, I set the max iterations to 100. You can set it to whatever you want. In fact, we'll try it with different values. Then we set an x1 list, so we can see how the our x inputs are changing, and we can see how our y inputs are changing. And then I just put in a loop from 0 to 100, and then we have basically our gradient descent. We're setting eta to 0.1, and then we're giving it the x we made up here, so our initial inputs, and then it's going to take that, and it's going to go get the gradient, and it's going to update the parameters, and it's just going to keep doing that over and over in a loop. Okay, so did I initialize this? Okay, so we're going to initialize this, and that should print out all the stuff that we need. Okay, so basically, I don't think it didn't print the original input. This is the second, or basically as soon as the inputs are updated, that's what it's showing us here. And then as we can see, as we go, they get lower and lower and lower and lower, and eventually we're going to wind up asymptotically close to 4 and 2, which is what we want. Because, I mean, it's hard to tell from the picture up here, but the 0 is at 4 and 2 is where that actually lives. And we can look at that from the original function, and we can say that, okay, I mean, we obviously see there's a 0. 4 minus 4 is 0. 2 minus 2 is 0. So it makes sense that the 0, or the lowest value, should occur at 4 and 2. Where input x1 is 4 and input x2 is 2. So, I mean, not really a surprise there, but it's neat that we can find it iteratively with gradient descent. And now, just to kind of visualize it, let's see what that actually looks like. So, again, we started up here with, what was it? Original values, 9 and 3. And again, remember, it's not going to start actually appending it to the list until the second value. So if it's not exactly at 9, so again, it's not exactly at 9, so it's probably just whatever the second value is, and the same thing here. But anyway, as we can see, it's slowly working its way down, and then we hit this point, and then we start getting asymptotically close to 4, which is good because for x1 it should be 4. We can tell that by just looking at the formula, or the original f of x equation. And the same thing here for x2, it goes slowly down and it gets asymptotic close to 2. So basically we've just used gradient descent to optimize a normal function off the street with 2 inputs. So pretty cool. Again, necessary in this case? Not really. But just to show that it can be done. I mean, it's not just a one-trick pony where we can only use it for data science. We can use this in a lot of different ways. Okay, and now let's change a few things. Let's say, okay, what if we make this? This is the learning rate, by the way. We talked about earlier. This is eta, or in this formula. In this formula it is alpha. So there's a lot of different ways that it can be notated or called, but it's the learning rate, and that's adjusting how fast we're moving towards the gradient. So let's just go, just for an over exaggeration, let's put this at 5. And let's see what happens. Okay, let's rerun the notebook. Okay, see, we way overshot. We're starting at 0, so we way overshot way down, and we overshot up, and we just can't make anything happen. Let's trim the iterations down. We'll see if we can get that zigzag pattern. That's what I'm trying to see here. Let's make it 10. Let's see if we can get the zigzag pattern with that. So kind of, again, all over the place. So what I'm trying to say is that it really makes a difference. Let's make this back at 100. Oop, that's 1,000. We don't want that. It's 100, and let's make this. Let's make it 1. Let's see what it is when it's just basically. This would be the equivalent of not having a learning rate. Doesn't work. Too big. Too big. All right. Let's see about. I haven't actually done this. This is the first time I'm messing around with these. So I probably should have done it before the video to save y'all time, but. Okay, I guess it just hops to the optimal solution. So let's take it back. Let's put it at 0.001. Okay, and we put it. Sorry, I just wanted to double check something really quick to make sure that that something wasn't wrong in the algorithm. But basically, we set it. It was originally at 0.01. If I set it to 0.001 at 100 iterations, it still hasn't even had time to figure out, what direction it wants to go. So basically, we look at it again. Sorry, let me rerun the whole thing. We get this straight line, and so it is advancing down. It's advancing towards the globally optimum solution, but not very fast. So if we move this to 1,000 iterations, oops, sorry, and we run it again, now we can see, okay, now it's going towards the optimum solution. If we make this 10,000, it should get there now. Well, maybe we made it too big, but there we go. See, and now it gets there. So anyway, just to show that the learning rate definitely plays a big part in how fast these things converge, whether they even will converge, in the amount of iterations that you've given. So actually, that mistake was a pretty good example of showing that, like, I thought something was wrong at first, but it wasn't. It just, I didn't have it tuned correctly. So anyway, good example of why learning rate is very important and what it can actually do. So there you have it, guys. I'm sorry this is a long video. I actually was hoping to make this shorter, but this is the crux, and to kind of get what we're doing after this is the most important. So all the videos after this will be shorter, but I just really wanted to hammer home a lot of points in this one so that it makes sense as we go forward, because it'll get more complicated. And I'm going to take it, in the next videos, I'm going to take it back to data science. So I'm going to take the problem, and then we're going to use the perceptron we created in the other series, and we're actually going to optimize that perceptron with these algorithms. So anyway, I know it's a lot. Thanks for bearing with me, and I promise the upcoming videos will be shorter. Anyway, guys, as always, if you enjoyed the content, please give me a like and a subscribe, so I can, you guys will know when I'm, putting new things out, and it'll help me, keep producing good content for you guys. Yeah. Alrighty, guys. I will see y'all in the next lecture, or I guess next video. Have a great rest of the day.